no algorithms in my talk. So sort of, when I wondered what I could talk about, what was really related, I didn't really see anything in my work. So I decided to talk about something different, because Skew braces are finite tolerant. I mean, there is model theory, there are groups, but no algorithms. 3 years ago, I was invited to a model conference, to a group theory conference in Caserta, and it turned out that most of the talks were about braces and Skew braces, and I thought that's quite interesting, and maybe one should look at the model theory. And shortly afterwards, I was contacted by Maria Ferrara and Marco Trombetti, who wanted to look at the model theory. They are group theorists in Naples and Caserta. And so we decided to write a first joint paper. Then I had a master student who is Moreno Invitti, who was looking for a subject for his master's thesis. So I gave him something on braces, which he solved very well. So he came for a thesis, and I thought, well, braces, that's not really standard, so I'll give him something else. Well, he solved his thesis subject during his first year, so I thought I'd give him something else. He did that the first half of the second year, and so I finally made him work on braces again. So this talk is a bit of an advertisement, I guess, for both braces and my student. So it's joint, but the main work was done by Moreno. So this is advertisement. So what's a brace? Oh, what's a Skew brace? A Skew brace is a set B with two laws, plus and times, such that it is additively a group, multiplicatively a group, and we have a funny left quasi-distributive law. A times B plus C is A times B minus A plus A times C. So we call it brace if addition is commutative. So we do not assume that addition is commutative. Now, if we have the usual identity elements, then 0 is equal to 1. They are the same. It's easy to see from the distributive law. And of course, we only have one-sided distributivity, so conjugation is not an automorphism. So this is very annoying. We call it brace trivial if addition and multiplication are the same or opposite. And it's easy to see that then the distributivity holds, which tells us that every group can be considered as a trivial brace or as an almost trivial Skew brace. They form a variety, so they're closed under the usual operations. There is an algorithm, and that's the only time I'm going to define the word algorithm in my slides, to calculate all the Skew braces of a given size. If we have a radical ring, then we can define a circle operation by A times B plus A plus B, and with that operation we get a brace. If we have a Skew brace, if we replace addition by the opposite, then it's still a Skew brace. And why do we look at Skew braces? Well, really, I look at Skew braces because it's fun. I want to do group theory, and here I have not only one group, but two groups. What could be better? But there actually are reasons to look at Skew braces, which come from statistical mechanics and the Young-Baxter equation, of which I know nothing, but here it is. So we have a vector space V, and we have a linear map RV tensor V to V tensor V, satisfying this Young-Baxter equation, and we want to solve it. And there's not only statistical mechanics, there's knot theory, braid theory, lots of other areas where this apparently intervenes. Drinfeld asked what happens if we simply, well, it's difficult to solve and there's no hope of classifying all the solutions, so what if we simplify? Instead of taking a vector space and a linear map, we just take a set and a map from V cross V, satisfying the corresponding relation. And now, and he called that set-theoretic solutions of the Young-Baxter equations. And now if we have a brace, then we get such a solution. Conversely, if we have a solution, well, a non-degenerate set-theoretic solution, we can construct a brace where the two operations are not inverses of one another. So this one is definable. Going back, we have to take something generated, so it's not a definable operation. So, the left distributive law tells us that the map lambda A, which associates, which maps x to minus a plus a times x, is an additive automorphism, and the map which associates a to lambda a is an homomorphism from the multiplicative to the additive group. We define a third operation star, which is minus a plus a times b minus b. In a brace which we have obtained from a regular ring, star is ring multiplication. In general, it needn't be associative, and of course, it measures how different addition and multiplication are. Now, additive subgroup is left ideal if it's closed under all the lambdas. It's strong if it's additively normal. It's an ideal if it's also multiplicatively normal. Left ideals are multiplicative subgroups, and left additive cosets are the same as left multiplicative cosets. But we know nothing on the other side. So unless we have an ideal, and then by normality, this also holds on the right, of course. And ideals, as in ring theory, they're precisely the kernels of two brace homomorphisms, and the homomorphism theorem solved. So we do have a way to talk about quotients of brace homomorphisms and so on. Okay, so that's skew braces. There were other undefined words in the title, finite Morley rank. So, a group G has finite Morley rank if there is an integer value dimension function for Morley rank from the collection of all non-empty definable sets in any arity, in any elementary extension of our group, satisfying that the Morley rank is at least n plus 1 if we find infinitely many definable disjoint subsets of Morley rank at least n. And in a group of finite Morley rank, the Morley rank of the union is the max, the Morley rank of a product is the sum, and the Morley rank of a map with constant fiber rank satisfies this additivity, which implies the preceding two, of course. So it behaves like a nice notion of dimension. And Morley rank, of course, was introduced by Morley in order to classify to prove Morley's theorem, stating when theories are uncountably categorical. But sort of soon people began to look at groups of small Morley rank. Let's say a group, as in geometry, is connected if it has no definable subgroup of finite index. And groups of finite Morley rank have the descending chain conditional definable subgroups, so there are connected components, minimal subgroups of definable subgroups of finite index. And Sherlin in 72, with final touch by Fréquent in 2007, 8, 13, classified all connected groups of small Morley rank. If the Morley rank is 1, then the group is abelian, either elementary abelian or divisible with finite n torsion for all n. If the Morley rank is 2, then it's either nilpotent or it has finite center, and modulo the center is affine transformations over some algebraically closed field. And if the Morley rank is 3, then either the group is soluble or modulo its finite center, it's PSL2K for some algebraically closed field K. And so we wondered, well, what are braces of finite Morley rank? Now, since we know what the additive and the multiplicative groups look like, how can they combine in a brace without augmenting the Morley rank? So the first thing is, we have an additive connected component, we have a multiplicative connected component, but there's no reason a priori why they should be the same. But stability tells us they are. So in a skew brace of finite Morley rank, the additive and the multiplicative connected component, they are the same, so they are an ideal of a finite index. So we can, every skew brace of finite Morley rank has a connected component, which happens to be an ideal. And then the connected skew brace of Morley rank 1 is trivial, and therefore it's a group of rank 1, which we know it's elementary abelian or divisible with finite integral. So these are easy. Now, what are rank 2? What are soluble? What is solubility? What is nilpotency for braces? Well, they are defined not in terms of commutators, but primarily not in terms of commutators, but in terms of the star operation being trivial. So we say a skew brace is soluble of derived length at most n if there's a sequence of ideals such that the product of a bigger one is in the smaller one. If we take the annihilator, it's the kernel of lambda. The kernel of lambda is where multiplication, where star is trivial. Or the A such that for all B, A star B is trivial. It's the kernel of lambda. If we intersect with the additive center and the multiplicative center, we get an ideal. It's called the annihilator. And then we can just iterate upwards. And we say B is annihilator nilpotent of class C if it's equal to the C annihilator. So just like the upper central series. Now, there are weaker versions of solubility which only require the i's to be left ideals or strong left ideals. And there are weaker versions of nilpotency where we don't intersect with the multiplicative center or don't intersect with the additive center either. And so there are loads of varieties what solubility and nilpotency could be. Now, in rank 2, there is a way to get soluble brace. We take a field. We take two homomorphisms from the multiplicative group to the additive automorphism group. And we endow the product k plus times k times with the direct product, with the sim-direct product along these morphisms. And that's a skew brace. And so the theorem is, if we are connecting skew brace of Morley rank 2, then either the brace is annihilator nilpotent, or it is soluble, and we know what it is. And in fact, up to reparametrizing, the phi plus and the phi times, they're just powers. So, so the A goes to A to the n. B goes to B to the m. And these have, obviously, if we take an algebraically closed field, then these are defined of rank 2 in there, so they are skew brace of Morley rank 2. And finally, if we have a skew brace of Morley rank 3, either it's soluble, or the annihilator is already the additive center, and it's also equal to the multiplicative center, and the quotient is PSL2K. Because it's trivial. So either B mod NB or B op mod NB op is PSL2K. What is used? Well, we use McIntyre's theorem. A field of finite Morley ranks are very closed. We use a field action theorem. If we have a group acting irreducible on an abelian group, we have an abelian group acting irreducibly on an abelian group, the action can be linearized. So these are old ingredients. The new one is that additive and multiplicative groups in a field of finite, in a structure of finite Morley rank are very different. So we say two groups are isogynous if they're finite index subgroups and finite quotients, such that the quotient and finite normal subgroups, such that the quotients are isomorphic. And then if we have two infinite fields in a finite Morley rank context, then there's basically no relation between additive and multiplicative groups. And yeah, that's the main ingredient in the proof of the third part. Well, actually already the second in rank 2. There are some references.